All right, here is another video on labs for Physics 1 or Physics 2, 1111 and 1112 mostly, although I may use these videos for 2211, 2212 in the future. So for my labs, there are 5 things that I want you to be able to do throughout the semester. Um, First one is collecting data. And so there are 2 aspects here. Avoid systematic errors in your measurements. That basically means don't make mistakes. And importantly, appropriately estimate the uncertainty in your measurements. Now, there's a lot going on in that little phrase, and there is a um, if you go to D2L and you look at the lab reference documents, there is a document here on measurement uncertainty, and this document has in it a um, flowchart that will be useful for you in determining the uncertainty in your measurements. Okay, there's also a video. If you go to the videos on lab skills, there's a video on uncertainty, which will also be helpful in understanding uncertainty and the uncertainty in your measurements. Okay, perform calculations with uncertainty. Again, there's a lot going on there. This is challenging. And again, there is a document here that has the rules that we use for doing calculations with uncertainty. And there is also a video doing math with uncertainty that gives some examples and will show you how to do that. Okay. Comparing numbers that have uncertainty. I haven't made a video on this yet. It's probably the easiest thing to understand. And again, there is a document in D2L that goes through how to do this. It's number 3, comparing with uncertainty. Lab skill 4 is plotting data using an appropriate title, axis labels, error bars, and curve fit. Curve fit there, again, being the exciting and interesting one. So pick an appropriate curve fit and show how it's related to the physics model that's being used in the experiment. That's a lot of what this video is about. And then interpreting curve fits. Determine if the model represented by the fit adequately represents the data, and use the values of the fit parameter to calculate something from your model. This is, again, these 2 are what this video is about. We do have, again, some documents on D2L that should be helpful, but this is maybe the most complicated part of doing labs this semester. All right. So let's look at an example lab. This is not a lab that we're doing in Physics 1111 or 1112, but it has all of the same aspects, all the same pieces of a lab that we might do. So in this example lab, we use a meter stick with a bunch of holes drilled in it to make a pendulum. And we put the pivot in different holes. So like if I put the pivot in this hole, we're going to have a really long pendulum. If I put the pivot in this hole, we're going to have a much shorter pendulum. Okay, so let me read it real quick. In this lab, a physical pendulum is made by drilling holes through a meter stick. The meter stick is suspended by a rod through one of the holes and swung as a pendulum. By placing the rod in different holes, the pivot point of the physical pendulum is changed from one rod to the next. The question is, how does the period of this physical pendulum depend on the distance from the center of the meter stick to the pivot point? And so every lab will have an introduction like this telling you what the experiment's about. Every lab will give us the physics involved. So for this experiment, we use the physical pendulum model. And we're going to treat the meter stick as a uniform rod. And this model predicts that the period of the pendulum, t, will depend on two things. Um, three things, I guess. G, the acceleration due to gravity, 9.81, we think that should be. Um, D, which is the distance from the pivot to the center of the meter stick. Very important. D is the distance from the pivot to the center of the meter stick. And L, which is the full length of the meter stick. And we end up with this equation that the period should be equal to 2 pi times L squared times 12 d squared divided by 12 times g times d. And how that equation was created, you don't need to worry about. What matters is this is our physics equation, or our physics model. This equation was derived using physics from the textbook, and it makes a prediction on how this pendulum is going to behave. So the first thing we have to do in every lab is take this physics equation, I guess here I call it the physics model equation, and the physics model equation is given to us here. But we need to convert this into what I call a fit equation. So a fit equation should be the same equation, but written in a way that a computer can understand. So a computer doesn't know what L is, and it doesn't know what D is, and it doesn't know what G is. So we need to change this equation into a fit equation. And the way we do that is we convert the independent variable to x, we convert the dependent variable to y, and then any remaining constants we have to collect together into a, b, and c. So the computer understands that x is the independent variable, that y is the dependent variable, and that a, b, c, and d, capital letters, represent constants that, so we need to convert this equation. The first thing we need to do is change the independent variable to x. So if I go back up here to the main question, how does the period of a physical pendulum depend on the distance? One thing depends on another thing. So the independent variable is the one that is causing the change, and the dependent variable is the thing that depends on the independent variable. So in this case, the independent variable is the distance from the center of the meter stick to the pivot point, and the distance from the pivot point to the center of gravity is d. So d is our independent variable. So what I'm going to do first, and you could do this with pen and paper. I'm doing it on my computer because it was the easiest way for me to do this right now. What I'm going to do first is everywhere I see d, I'm going to change that to x, because I know that x is supposed to be my independent variable. Then my dependent variable is supposed to be y. And my dependent variable is the period of the physical pendulum. And the period is t. So that means t is my independent variable. Okay, so that was my first step. I take my independent variable and I convert it to x. I take my dependent variable and I convert it to y. The next step is to collect any constants. Now, anything that's an exact value, I can leave alone. If it's an exact value, it's already fine. I can just leave it in there exactly as it is. Okay? Anything that's an inexact value, in this case, like L, or G, needs to be collected into one of these constants, A or B. So here that L is an inexact value, and L squared is also an inexact value. So I actually have a choice. I could just change L into A. So then instead of L squared, we have A squared. But actually, I'm going to take this whole thing, A squared, and call it A. So, so what happened is I took L squared, um, I took L squared and replaced it with A. See, this L squared here became this A. So my L squared became an A. Okay? And then the next thing I'm going to do is take care of this G. And what I'm going to do, so let's rewrite this equation. So I could just take that G and call it B. I'm actually going to do something different. I'm going to take the whole thing, I'm going to take the whole thing 12G and convert that into B. Okay, so what did I convert into B? I converted 12G into B. So where I used to have an L squared, now I have an A. Where I used to have a 12G, now I've got a B. So the resulting equation is y equals 2 pi times the square root of a plus 12x squared divided by b squared. And the 2 pi is okay to leave in there because it's an exact value, and the 12 is okay to leave in there because it's an exact value. Any other constants need to become part of the a or the b. Now I'm also going to rewrite this, I see, as 2 times pi times the square root of a plus 12 times x squared divided by b times x, close parentheses, close parentheses. So this is how we do square root in a computer. And we are taking the square root of everything that's currently in gray. I can tell because we've got an open parentheses and a closed parentheses outside the gray. So what are we taking the square root of? Well, we're taking the square root of a fraction. Everything in here is on top of the fraction, a plus 12x squared, and everything down here is on the bottom of the fraction, b times x. So it's important in the computer, you have to put in a star for multiplication. You have to use a caret for exponents. You have to use parentheses when you're making a big fraction. If you've got a complicated fraction, make sure you put the denominator of the fraction inside a set of parentheses. Make sure you put the numerator of the fraction inside of the set of parentheses. Okay, so this is how we create our fit equation from the physics equation. Now, a lot of yours are going to be much, much, much simpler than this. You may end up with a fit equation that's just a times x, or ax plus b. But this was a complicated one for our example. Okay, the next step in your lab is going to be collect the data. I stole some data from a student that did this lab several years ago, and the student actually didn't use a meter stick. They used a ruler, like a 12-inch ruler. And so the 12-inch ruler had a length of 30.5 centimeters, which is 0.305 meters. And that'll matter. Later, they didn't actually use a meter stick, they used a ruler, but it doesn't matter. The physics is very similar. Okay, so you're going to collect your data. So they did a value for D, a value for, and then measured the period for all of these different distances. And you're going to need to justify your uncertainty, but that's a different video, so we'll talk about that later. Let's just assume that these uncertainties, the students determine these uncertainties and that they are correct for this lab. Okay. The next thing every lab will have is an analysis section. So the first part says, graph your data with PhysicsPlot and include it on a separate page. You should include the main graph, the residual graph, the chi-square, the fit equation, and the fit parameter. All right, so let me show you how to do that. We go into PhysicsPlot, physicsplot.com, and this is a website that I created for my physics students so that we could do these labs. So the first thing you're going to do is just put in your data. We can give a label for the x-axis. So in this case, x is going to be our distance. And we've measured that in meters, so I'm going to put the units after the thing. And then we put in our x values, 0.0254, comma, 0.0381, comma, 0.0508. That's getting really tedious. Let me just put in the first three for now. 0.001, comma, 0.001, comma, 0.001. Next thing we do is put in our uncertainties. We have to type them all in because they could all be different. So if they're all the same, you just have to type it in over and over and over again. The y-axis is going to be my period measured in seconds. And my first three values there are 1.129 and 1.004 and 0.891. And my uncertainties are 0.01, comma, 0.01, comma, 0.01. And I hit load data. And if I typed everything in correctly, I'll get a table over here showing my values, my uncertainties, my y values, and my y uncertainties. And if I didn't type it in correctly, what's going to happen is the website's going to crash, and you're going to have to start over completely and type it all in again. And that's really going to suck. And you really don't want to have to do that. So let me show you an important extra feature. If you just click load data on the default data that's in here and you click download CSV, that's going to create a file called physicsplot.csv, which you can then go in and edit. This is an Excel file. It's not a normal Excel file. It's called a CSV, comma separated value file, but it has this format where row 1A is the X label with units. Row 1C, this one's blank. Row 1C is the Y label with units. Row 1D is blank. And then in row 2, we start putting in our data. These are the X values. These are the X uncertainties. These are the Y values. These are the Y uncertainties. And what you can do is just type in your stuff from your lab, right? Distance in meters, period in seconds, and then 0.0254, 0.0381, 0.0254. Okay, and so on and so forth. And I've already done that. And here is what that file looks like. So this is all of the data from my lab. So I'm going to go ahead and save that. And now, if I go into PhysicsPlot and I browse, and I go to my downloads folder, there's my physicsplot.csv, and I hit populate. And what it does is it types in all those numbers for me. Oh, interesting. I see that these are not the values from over here. So let's go fix those. 0.01, 0.01, 0.01, 0.01, 0.01, 0.01, 0.01, 0.01, 0.01. Save that. Let's do this again, populate. And now we've got all the correct values in here. And if I hit load data, this data table over here should be the same as the data table in my worksheet. Okay. Next in PhysicsPlot, we're still working on making a good graph. So we need a title. This might be ruler pendulum. We need to put in the minimum and maximum values. So let's look at our data table. If I can, I always like the x minimum value to be 0 and the x maximum value to be a little bit bigger than the biggest number that we used. So in this case, I'll use 0.15. I like the y value to be 0 if possible, and the maximum to be a little bit bigger than the biggest value. Looks like maybe 1.2 would work well here. And then just now, all I'm going to do here is click just data, and that's going to create a graph that shows my data points. And the reason I'm doing that is just to look at the maxes and mins and see if I think it looks pretty. I actually think this will look a little bit prettier if I go up to maybe 1.4. Just data. Okay, and that's what my graph with just the data is going to look like. All right, next thing is to put in the fit. So we want this equation. So 2 times pi times the square root of a fraction, right? So you see I've got the square root of the blue thing, and the blue thing is a fraction. And the top of my fraction is going to be a plus 12 times x squared. And the bottom of my fraction is going to be b times x. Okay, and then I'm going to click manual fit. And the reason I'm clicking manual fit is I just want to test, did I type this in a way that the computer could read? Because, for example, if I had forgotten to put in that multiplication sign and I did manual fit, I would get an error. And that would mean there's something wrong with the way I typed in my equation. So let me get that multiplication sign back in there. If I click manual fit and it doesn't give me an error, then I know I've typed in my equation fine. So the next thing I'll do is autofit, and usually that's going to just work. And here it did, it just worked. Okay. Occasionally that will give you an error, and I guess if that happens, just call me over and we can fix it. But okay, so it seems to have worked, and what it did is it adjusted the values of A and B until it found the best possible value for our data. So it could have used any value it wanted for A, any value it wanted for B. It tried all of them, figuratively speaking, in computer language. It tried all of them, and it found the one that was closest to all of our data points. And what it'll do now is it'll tell us what values those are. Okay, so it tells us what values those are, what it thinks A should be, and what it thinks B should be. It also tells us the uncertainty in A and the uncertainty in B. So this is what we're going to want to put into our lab report. And I can do that by clicking this button. It creates a, whoops, I didn't want to do that. That's going to take forever to load. Oh, not that long. It creates a, an image that we can put into our Word document. So if I open that up, I can either just So I can put that right into my Word document here at the end. Okay, and now I've got my graph, because the directions say graph your data. You should include the main graph, the residual graph, the chi-squared, the fit equation, and the fit parameters, and we put that on a separate page. Okay, is it a good fit? That question we will talk about in class. And there is a document on D2L that helps you determine if it's a good fit or not. There are really two important questions. The first important question is, we look at these residuals, and I don't want to get into all the details here because we'll talk about it in class, but the residuals tell you how far away each data point is from the line. See, this data point's below the line, this data point's below this line. This data is above the line because that one's above the line. This one's below, above, above, below. And those three are pretty much right on the line. Okay, and so this is like zooming in and seeing how far away each data point is from the line. So there are two things we want to look at when we look at this. The first thing we want to look at is, are they random or does it show a clear pattern? And there are three clear patterns we want to look for. Either all above the line or all below the line. That would be a clear pattern. A clear downhill pattern or a clear uphill pattern. That would be a clear pattern. We could have a smiley face or a frowning face. That would be a clear pattern. If we don't have any of those, we'll just say it's random. You could think that maybe you see a more complicated pattern and be like, well, first it goes up and then it goes down and then it goes up and then it moves to the left and then it moves right. It's probably not a pattern. Okay, so this one looks random. The next thing we look at is the chi-squared. Chi-squared here is a number that tells you, on average, how far away are the data points from the line. And a good number for chi-squared should be close to the number of degrees of freedom. And what does it mean to be close? Well, close to means plus or minus the square root. So if I take the square root of 8, it's 2.8. So if this number is between 8 plus or minus 2.8, then it's a good fit. If the number is bigger than 8 plus the square root of 8, then it's not a good fit. So this one is a good fit. So was it a good fit? Justify your answer. Remember, there are two things we have to say. We have to look at, are the residuals random, and how big is the chi-squared? You have to talk about both of those things when answering this question. So for this one, I would say it is a good fit because the residuals are random and the chi-squared is 8.3 with 8 degrees of freedom. This is okay. If the chi-squared was bigger than, let's see, 8 plus the square root of 8 is 10.8. If the chi-squared was bigger than 10.8, it would not be a good fit. Okay, so there we answered the first question, was it a good fit, and we justified our answer. What does this mean about the assumptions that were made when generating the physics model? Well, because it's a good fit, the assumptions in the physics model worked for our experiment. So whatever assumptions were made in creating that physics model, they worked fine for our experiment. If it had been a bad fit, we would say, well, there was either something wrong with the assumptions in the physics model, or there was something wrong with the data collection. Okay, next, determine the experimental value of the acceleration due to gravity from the values of A and B in your fit. Okay, this is critical. This is where everybody likes to make mistakes. First thing first, we are not going to plug in any of these numbers into anything. Period. End of story. We are also not plugging anything into this equation. Period. End of story. Here's what this is asking. Determine the experimental value for the acceleration due to gravity and the length of the ruler from the values of A and B in your fit. Include uncertainty in your calculation. So here's what happened. A was equal to L squared because we took L squared and replaced it with A. And then what the computer did is it tried every possible value of A and came up with the very best one. By trying every possible value of A, what the computer was kind of doing is trying every possible value of L, the length of the ruler. And it found the best possible length of the ruler. The best possible length of the ruler was the one where L squared was equal to 0.090747835. So I'm going to start with A is equal to L squared. A is equal to L squared. And from that, we are going to determine, by the way, this insert equation feature in Word is really cool. It has fractions and square roots and all kinds of cool stuff. Well, from that, we can learn that L is equal to the square root of A. Okay. So, from that, I don't like that it's still highlighted. Stop being highlighted. Okay. So from that, we learn that L is equal to the square root of 0.90 or 0.090.090747853. Okay, and I'll go ahead and do that too on here. L is equal to the square root of 0.090747583. Nope, 853. Which is equal to, according to my calculator, 0.301244 meters. Okay, so we have calculated L from our value of A. Next, we need to know what's the uncertainty in L. And there's a whole video on doing this, so I don't want to go into the whole thing. But if we look at this equation is the same as A raised to the 1/2 power. So what that means is, using Rule 2, and again, go to the videos, we know that the uncertainty in A divided by A, the uncertainty, I did this in my notes too, the uncertainty in L over L, we are looking at this equation. The uncertainty in L over L is equal to the uncertainty in A over A But since a is raised to the 1/2 power, we have a 1/2 that we put in front here. Okay, so that means that this is equal to 1/2 times the uncertainty in a, which we find over here, 0.003683913 divided by a, 0.090747853. Okay, I like that. That will look better with the 1/2 out in front. Okay, so that is equal to, plugging this into my calculator, 0.5 times 0.003683913 over 0.0907. Oops. 747.853. So this is equal to 0.020298. And we're not done yet, because to find the uncertainty in L, we still need to multiply both sides by L. So this means that the uncertainty in L is equal to 0.020298 times 0.301244, which is equal to 0.006115. Okay, so we've calculated L, we've calculated the uncertainty in L, and now we're ready to write down L. Oops. I hope you're watching this in 2x. L equals 0.301224 plus or minus 0.006115 meters. Okay, and now significant digits. And again, this is in a video. We start by looking at the uncertainty. And the uncertainty will either have 1 digit or 2 digits. In this case, it will have 1 digit because we look at the first 3 digits, and if it's between certain values, we either keep 1 or 2 digits. In this case, we'll keep 1 digit, so 0.006. Now, we see that this has 3 digits after the decimal, so this one should also have 3 digits after the decimal. So 0.301 plus or minus 0.006 meters. That's what we think. That's what PhysicsPlot thinks the length of the meter stick is. And the reason PhysicsPlot thinks that is because it tried every possible value of A, and it found the one that fit our data the best. And we know that A is equal to L squared, so if we know what A is, we know what L is. I hope that makes sense. All right, next let's look at G. So I'm going to go back up here, and again, I'm not plugging in anything into this equation. I'm not plugging in any of these numbers anywhere. I'm just looking at how is G related to A or B. And G is related to B. And what I have is that B is equal to 12G. So I'm going to come down here and I'm going to say B is equal to 12G, which means G is equal to B over 12. Okay? Which means that G is equal to 114.905306 114 divided by 12, which means G is equal to 9.57544 meters per second squared. Okay, that's great, but how do I find the uncertainty in G? Well, we are dividing by an exact value, 12. So this is actually rule 1. And if you go to the videos on doing math with uncertainty, rule 1 will tell us that for this situation, the uncertainty in G is equal to the uncertainty in B divided by 12, which in this case is going to be equal to 2.607460380 divided by 12, which is equal to 2.607460380 divided by 12, 0.217.288. So this is our uncertainty in G. So that means that G is equal to G equals parentheses 9.57544 plus or minus 0.217288 meters per second squared. And now significant digits. Again, we start with the uncertainty first. Look at the first 3 digits. It's in a specific range that tells us we need to keep 2 digits. So the 2 digits we're keeping are 0.22. Now, this has 2 digits after the decimal, which means I also need to keep 2 digits after the decimal here. So we're going to round that to 0.58. So 9.58 plus or minus 0.22 meters per second squared is our G that we calculated from the value of B that we got from PhysicsPlot. And remember, what PhysicsPlot was doing, it was trying all possible values of B. And when it was trying all possible values of B, it was like it was trying all possible values of 12G. And once it found the one that it liked, it kept it. And that value, 114.9, was equal to 12 times G. So in order for us to find G, we had to divide it by 12. Hope that makes sense. All right, finally, does your experimental value of G agree with the accepted value of 9.81 plus or minus 0.01? Use t-score to justify your answer. And again, we have a reference document comparing with uncertainty that tells us how to use t-scores to answer a question like, do these 2 numbers agree with each other? So the thing we do here is we calculate a t-score. And the t-score is equal to G measured minus G expected divided by the uncertainty in the first G plus the uncertainty in the second one. Now, you might ask, does it matter which one goes first or which one goes second? The answer is no, because this is at an absolute value. So we always just find the positive value. So in this case, this is going to equal this is going to equal 9.81 minus 9.58 divided by the uncertainty in 9.81, which is 0.001, plus the uncertainty in 9.58, which is 0.22. So that's equal to 9.81 minus 9.58, which is, oh, that's fun, 0.23 divided by, and it just sort of magically turns out here that we also got 0.23 for the denominator, so our t-score is exactly 1. Okay, and again, comparing with uncertainty, if you go to this reference document, it will tell you how to interpret different t-scores. If it's less than 1, if it's between 1 and 3, or if it's more than 3. This one's funny, it's exactly 1, so which one does it fall into? I guess if it's exactly 1, that's between 1 and 3, that's not less than 1, so it's not clear from the data if the values are in agreement or not. Is it in agreement? Well, with a t-score of 1, it's not clear if it agrees or not. It might agree, it might disagree, which is okay. That's a result that we can live with. If we got that it definitely disagreed, then that would be a surprising result because we think G really is 9.81, and so if our data gave us a different G, that would be weird. But it didn't. So what I'm going to say here is, according to our t-score, we cannot be certain if the experimental value of G agrees with the expected value of G or not. We cannot be certain if the experimental value of G agrees with the expected value or not. Okay, that is the process of doing a lab. If you do your lab in pencil, then or on paper, then of course that's fine. Whatever you turn in is fine. If you do it in Word, it would be really helpful for me if you put everything that you typed into the report in red, so that it's then very easy for me to go through and find the stuff that you typed into the report, so that I can grade it. Here is my answer on uncertainty. Okay, that's something that I would need to type into the report if I was turning this in, so I'll put that in red. Of course, you're actually going to answer the question, not just say, here's my answer. So then everything that you typed in is in red, and now that's ready to save and turn into D2L. All right. I hope the video was helpful.